Hello guys, this video is going to be about the angular momentum. In the previous videos I discussed the linear momentum. This video will be about the angular momentum part 1. Now the angular momentum is a physical quantity symbolized by the letter sigma, which is the multiplication of the inertia of the particle or the object with its angular speed represented by the quantity theta prime. Now the inertia I for a particle is equal to the mass of the particle multiplied by the distance squared. So which means that if we have, this is an axis about which a particle called S rotates. So therefore this is the R, where R is a distance separating the particle from the rotating axis. So this particle is rotating in this way. So this is R, which is the distance separating the particle S and the axis of rotation. Then the inertia of this particle will be its mass multiplied by the distance squared. Now if we have a system of particles that are rotating about an axis delta, so sigma will be, because we have many particles, so we have to sum up all of their angular momentum. So will be the summation over I from 1 to n, where n is the total number of particles rotating around the axis delta. So will be I, which is the inertia of each particle, multiplied by theta prime, the angular speed of each particle. But as you know, for a rigid object, all particles are heading with the same direction, so they have the same angular speed. So all particles are moving with the same angular speed. So then theta prime will be common as all is common for all particles. So we still have I. So we get that sigma is equal to theta prime I, where I is going from 1 to n. So as we said, because all particles are having the same angular speed, so we can take out of the summation theta prime I as a factor common for all of particles, and we still have I right here. But the summation of each, so the summation of the inertia of each particle from I equal to 1 till n, we get I total of the system. So sigma will be theta prime I total of the system. So therefore the angular momentum for a rigid solid S in rotation is equal to I theta prime. Now this quantity sigma might be positive or negative depending on the angular speed. So sigma will be positive if theta prime is heading in the plus VE direction, then sigma will be positive. Now the angular momentum sigma will be negative if the angular, or if the particle or if the object are heading in the negative direction. So if sigma in the negative VE direction, where the positive chosen direction is anti-clockwise, and this is the positive chosen direction. So if the particle is heading in the negative chosen direction, therefore sigma will be negative. And if the particle or the object is heading with a positive direction, then sigma will be positive. So sigma is an algebraic quantity depending on the angular speed that the object or that the particle are heading through. Now, back to Newton's second law. Newton's second law states that the net F external is equal to the mass of the object multiplied by its acceleration. In rotation, instead of the force F, we use the moment of a force, which is equal to sigma moment of F is equal to, so it's an analogy, M in translational motion, instead we use I, which is the inertia of the object or of the particle, and A is theta double prime. Now, as we said in translational motion, F external, in rotational motion, instead of Fx, we use moment of the net F external, which is equal to I theta double prime, where the moment of a force is equal to the force itself curled with the distance, and its quantity is equal to the force multiplied by the distance away from the axis of rotation multiplied by the angle alpha between the force and the distance away from the axis of rotation. So if we have here the axis of rotation, and we will have a rod, and this is the rod, and we apply a force F, then the moment of F will be equal to F cross D, which is, and its quantity is F multiplied by D multiplied by the sine alpha, where alpha here is 90 degrees, and D here is a distance, and D here is a distance between the axis of rotation and the point where we are applying the force F. So this will be its quantity, and through the right hand rule, we can see that the moment of the force F tends to rotate the rod in this chosen direction. Then this rod is moving or it's moving in the negative chosen direction. Then the moment of the force F will be negative because it's tending to rotate the rod in the negative chosen direction. Because this is the positive chosen direction, this force F is tending to rotate the rod in the negative direction. So its moment will be in the negative direction. Now let's go back to momentum. So as we said in the previous, we have a mechanically isolated system where the net F external are zero. Instead we can use sigma moment external. If they are zero, we can say that this is a mechanically isolated system, which leads to sigma initial equal to sigma final. By this we mean that the angular momentum is conserved. Now let us take an example about a belly dancer. Therefore, the system is a belly dancer of stretching arms. Therefore, the external forces acting on this dancer is only its weight or her weight, sorry, and the normal reaction. So, and this is the axis of rotation. So, because these two forces are passing through delta, therefore mu So in the next video, I'm going to continue the example about a belly dancer stretching and unstretching her arms.